Hello and welcome to Lecture 3 of Circuits in PHYS 1201. We spent the last lecture looking at circuits made basically entirely of resistors. Now we're going to bring capacitors into the mix. So we're going to do exactly what we did for resistors and figure out ways to reduce capacitor circuits to simpler circuits. So here we have two capacitors in series, and we're going to reduce this circuit to this form, where now remember that the charge is what's related to the voltage across the capacitor, not the current, and so it's going to be convenient to work with this. And so here in this simple circuit, we know that the voltage rise you go through going through the battery has to be the same as the voltage drop you go through in the capacitor, and so this is the relationship. And so we're going to take a loop law, just like we did for the resistors, and use it to figure out what this equivalent capacitance is. So the loop law just says that epsilon minus Q1 over C1 minus Q2 over C2 is 0. But now let's think about these Q's. Because what happens is that really it's electrons moving, right? But I'm going to, as usual, pretend that it's positive charge. So positive charge flows off of the bottom plate of C1 onto the top plate of C2. And positive charge flows off the bottom plate of C2 and eventually arrives around at the top plate of C1. But that means that whatever charge is here on this plate, it came from down here. And likewise, whatever charge is here, it came from up here. And so the charges on these capacitors have to be the same. Q1 equals Q2, which is just what we're calling capital Q here. And so we can just rewrite this epsilon equals, which is Q times 1 over C1 plus 1 over C2. And if we compare that with this, I could write this as Q times 1 over C equivalent. And now you can see that we have a relationship that looks a lot like resistors in parallel. Things are flipped around compared to resistors. For capacitors in series, we add the reciprocals, like so. And again, it's not restricted to two capacitors. This would work for any number of capacitors in series. So now let's do the same thing for capacitors in parallel, and I'm going to work through this pretty quickly because it's pretty much all stuff you've now seen several times. Same sort of arguments. So I'm going to do my loops. And then the junction. Well, one way of thinking about it is that over here, Q is the total charge that flowed through the battery in the process of charging the capacitor. And so here, whatever charge flowed through the battery got split between the two capacitors. And so we have that Q is Q1 plus Q2. So I'm going to rearrange A and B, and then I'm going to plug them in up here. And I'm going to solve for epsilon, so I have an equation in the same form as this one. And again, you can now pick out what C equivalent is. C equivalent is C1 plus C2. And again, this would work for more than two capacitors in parallel. So let's now do exactly what we did for a resistor circuit and analyze this circuit. In a resistor circuit, what we were trying to find was the currents. In a capacitor circuit, what we're now going to try and do is find the charges. Because if we know the charges and we know the capacitances, we can then find everything else. So we're going to do exactly the same thing. We're going to progressively simplify it. So the first thing here is we have these two capacitors, C2 and C3, that are in parallel. And so that means they are going to reduce to an equivalent resistance that I'll call CA. And they're in parallel. And for capacitors, resistors in parallel just directly, or capacitors in parallel just add. So C2 plus C3. And so that's just 6. microfarads. And at that point, our circuit just looks like that. So now we just have these two capacitors in series, and so they are going to combine into an equivalent resistance that I might as well call CB. And 1 over CB is going to be 1 over C1 plus 1 over CA. That is 2 over 6 plus 1 over 6. That's 3 over 6 microfarads is 1 over CB. And so CB is just 2 microfarads, just flipping that. All right, and at that point, we're done reducing it. We are down to a single capacitor. So now we work backwards. We say here we have this loop, which tells us that epsilon is some QB over CB, and so that gives us our QB. We can just say QB is CB, which was 2 microfarads, so 2 times 10 to the negative 6 farads, times epsilon, which was 12 volts, and so that is 2.4 times 10 to the negative 5 coulombs. Now, that turns into, as we rebuild the circuit, that turns into CA and C1, and they were in series, and so they have the same charge on them, and so this is QB is Q1, so we've now found Q1, and it's also QA. That's going to allow us to find the voltage across the capacitor A. So I'll say delta VA is QA over CA, which is and so that now is going to let us find Q2 and Q3 because delta VA is just delta V2 and delta V3. And so that's that. We can say Q2 is C2 delta V2, and we can plug this number in. And similarly, Q3 is just going to be C3 delta V3. And so we can plug the 4 volts in again, and we'll get those charges. Just as before, you could analyze a circuit like this using Kirchhoff's laws directly. So I'm going to define a loop A and a loop B and just show you how to set it up. I'm not actually going to work through all the algebra. So there are 2 loops, and then I'll pick a junction. The junction law, there's a little trick to it here. So doing those loops, epsilon minus Q1 over C1 minus Q2 over C2 is 0. And then loop B, epsilon minus Q1 over C1 minus Q3 over C3 is 0. And now we get to the junction. Now, we know the junction law as the current in equals the current out, but you could also think of it as the total charge that comes in as the same as the total charge that goes out. And so these 2 capacitors, you can think of them as charging in part because charge comes off the bottom plate of C1 and flows down onto the top plates of C2 and C3. And so the way the loop law plays out here is that Q1 equals Q2 plus Q3. And so now we have 3 equations in 3 unknowns, and we can solve this. We're going to finish up this unit looking at circuits that contain both resistors and capacitors, which we call RC circuits. And so here's an RC circuit. This is about the simplest you can put together. There's no battery in it, but let's imagine that we've previously charged this capacitor up, perhaps by connecting it to a battery. We've now disconnected it and hooked it up to the resistor like this. And so there's a voltage across it because the voltage across a capacitor is related to the charge on it. And right now, no current can flow because this switch is open. But if we close the switch, then current will flow. Current will flow off of the top plate through the resistor and onto the bottom plate. And we can do a loop law going up through the capacitor. There's this voltage rise. We come around, we go down through the resistor with the current, so that's a voltage drop. And there's our loop law. And now, because this current is flowing off the top plate, that is reducing the charge. And that charge is related to the voltage across the capacitor, so that's decreasing. And the loop law tells us that voltage is the same as the voltage across the resistor, and so that voltage is decreasing as well. And Ohm's law tells us that voltage is related to the current, so the current is decreasing. So we have a time-dependent current. Working out exactly what the time dependence is requires some fancy calculus, so we're not going to do it, but I'll just show you it comes out as an exponential decay. And the thing that's useful about this is that the time constant in this exponential decay, which is the time it takes for the current to decrease to 1 over e of its original value, is directly related to the resistance and the capacitance. And so RC circuits are used a lot in building circuits that you use for timing things. Here is a much more complicated RC circuit. And let's just think about what happens. We've got our battery, our two resistors, an open switch, and let's say that this capacitor starts off uncharged with some Q0 that is 0. Well, so initially it's just as if this whole branch here isn't here at all because that switch is open. And so all the current that goes through R1 would proceed to go through R2. And we could solve for those currents pretty easily, but we're not going to. We're instead going to think about what happens when we close the switch. And so again, I'll say that the charge is 0. We've just closed the switch. And so now we're going to have current, although we'll have to talk about that in a second, and a current IC coming this way. And let us write loop laws and junction laws. Okay, now these loop laws and this junction law are true all of the time after we close the switch, but there are a few special things going on. So at the moment, Q is 0, and so that tells us so is delta VC, right? The voltage across this capacitor is also 0, but it is in parallel with R2. And so the voltage across R2 is 0. And if the voltage across a resistor is 0, then there's no current running through it. And so at this moment, when Q is 0, that means that I2 is also 0. And so all the current runs this way to the capacitor. And we could now work out what that current is quite easily. Now, things get complicated after that. We'll still have our current this way and our current this way, but as charge now starts to build up on here, that means the delta V, the voltage across this capacitor, delta VC grows, and so does delta V2, and so I2 grows, it's increasing. And the way it does that in time is sort of complicated. But what is simple is that much, much later, the capacitor will be fully charged. And so much later, no more charge flows to the capacitor, and so IC is 0, at which point I1 equals I2, which then you might as well call I. And you could now come back up here, plug I1 equals I2 into here, find that current, come down here, find what the voltage is across the capacitor, and charge for its and solve for its charge at that